Today we're going to discuss about chelate effect on John-Teller distortion. Here we're going to see how the chelate effect is affecting on the stability by John-Teller distortion in chelated complexes. So if you see the complexes are having the D1 or D9 electron configurations which will undergo distortion to get the stability. That is called John-Teller distortion. So for example, if you see the copper 2 complex having the D9 system, it will undergo the distortion to get the stability. That is called John-Teller distortion. But in chelated complexes, the chelated complexes have a tendency to restrict a metal complex from undergoing the distortion. So therefore, here there is no stability due to John-Teller distortion. If you see the equations, so in first equation, the one ethylene diamine molecule is replacing the water molecules. Okay, so it is getting some chelated complex. Okay, so the stability constant is concentration of products and the concentration of reactants like this. Okay, next, if we see to this product, again we are adding the ethylene diamine ligand, right? So here two ethylene diamine molecules were added and two water molecules are there. So if we see the stability constant, the concentration of products and concentration of the reactants will be like this. If we see in equation 3, again we are adding one more ethylene diamine to this product. So it resulted the tris-ethylene diamine metal complexes. That means purely chelated complex. Of course, it is also chelated complex, but monodentate ligands were present in equation 1 and equation 2. But in equation 3, there is no monodentate. All were three ligands are bidentate ligands. Therefore, K3 can write as the concentration of products and the K concentration of reactants like this. If we see the graph of K1, K2, K3. If we see for K1, K2, K3 for the different metal ions, manganese, iron, cobalt, nickel, copper and zinc. If we see the K1 profile, it is increasing by going to manganese to iron, iron to cobalt, nickel, copper and zinc like this. K2 also in the same fashion it is going. But when coming to K3, it is increased manganese to iron, iron to cobalt, cobalt to nickel, but it has suddenly decreased in the case of copper. And it will go like this. That means K1, K2 has increased in case of copper 2 ion, which is having the D9 system, but the K3 has decreased. Because if you see the K1 product, K2 product, K3 product. In K1, it is chelated, but 4 monodentate ligands are there. 2 aqua ligands, monodentate ligands along the z-axis are there. Here, the aqua molecules were present, monodentate ligands were present along the z-axis. So, here is the possibility to undergo distortion to get the stability. Therefore, K1, K2 is increased in case of copper 2. But in case of K3, what happened? All ligands are chelated ligands, right? Bidentate ligands. Therefore, it is chelated complex. So, all rings are having the fixed bite. So, all rings are will be under strain. So, all rings are under strain. Therefore, there is no possibility to undergo distortion. So, K3 is decreased in case of copper 2 ion. So, due to chelate effect, here having the bidentate ligands, therefore there is chelating effect is not permitting to undergo distortion. Therefore, in case of copper 2, K1, K2 increased due to John-Teller distortion along the z-axis, where K3 has decreased due to chelate effect, no distortion along the z-axis, because all the rings are under strain and they having the fixed bite and not allowing the distortion.